In this lecture, we will be discussing cryptography and how it is used in cryptocurrencies such as Bitcoin. First of all, what is cryptography? Well, cryptography uses many advanced mathematical techniques to disguise the data. This is used to prevent tampering, and the key point that we will be discussing is the use of hash functions. And what is a hash function? A hash function is a mathematical function that has three distinct properties. First of all, it can take a string of input of any size and it produces a fixed number output. And for our applications, we will be using 256 bits. In addition, it has to be efficiently computable. This means that given a reasonable amount of time, the output can be determined. Also, in order for a hash function to be cryptographically secure, they need three other properties as well. They must be collision-free, they must have a hiding property, and they also must be puzzle-friendly. And in order for it to be collision-free, it means that no one can find the value of x and y such that x and y are different and that the hash of x equals the hash of y. In other words, if the values of x and y are different, the hash of these values will not be the same. One thing to note is that the collision cannot be found, not that it doesn't exist. Collisions do exist because of the infinite number of inputs, but only a limited number of outputs. The key is, are they findable by regular people with a regular computer? Now, how would you find a collision? There are ways to find it. One of these that is guaranteed to work is if you try 2 to the 130th power random inputs, there's a 99.8% chance that two of them will collide. However, that many random inputs would take entirely too long to even matter. So there are no hash functions that have been proven to be completely collision-free, only that almost impossible to find these collisions. Now, why do we need hash function to be collision-free? Basically, if we know that x and y have the same hash, we can assume that the values of x and y are the same. So another way to look at this is if we want to recognize a file by its 256-bit hash instead of looking at the entire file. This is a lot easier to look at because the hash will be smaller than the entire size of the file. So the next property is hiding. So what does that mean? Well, if we know the hash output, then there is no way to determine the input. However, this property doesn't exactly hold true. If there are only a few possible values of x, then we would be able to compute the hash for each one and determine what it would be. Therefore, we must have a high min entropy for this to have a hiding property. In other words, the distribution must be very spread out and completely random. A real-world application of this would be taking a value and sealing it in an envelope and placing it on a table for everyone to see. You have then committed to this value, and when it is opened up at a later time by someone else, the value is then revealed. This is what we want to do. Commit to a value and reveal it later. And this is what the application programming interface would look like for the envelope example. You can commit to a message, and that will produce a key to unlock the commitment. Then later, someone can verify this commitment by using the key that you have given them. The next thing we'll talk about is puzzle friendliness. So if someone wants to target the hash function to come out at some particular output value of y, that there's part of the input that is chosen in a suitably randomized way, it's very difficult to find another value that hits exactly that target. So, what does that mean? We can use this property to create a search puzzle that ensures that there is no better solving strategy than trying random values of x. This will be very important when we start talking about mining cryptocurrencies. Now, the particular hash function that is used in Bitcoin is called SHA-256. It's a very popular hash function. It's commonly used in cryptocurrencies, and it can take any length of input, divide it into blocks, and perform the calculations, and the results are in 256-bit. Here is an illustration of how this hash function operates. And you can see the blocks are divided up and the results are in 256 bits. Next, let's talk about hash pointers. A hash pointer points to where something is stored along with a cryptographic hash of the information. This allows us to ask for the information back as well as verify the information hasn't changed. This proves useful as a tamper-evident log, such as a blockchain, which is a digital ledger of the transactions. Each of these blocks will contain hash pointers to the previous block. This is also sometimes known as a Merkle tree. And here is an example of how a blockchain would look. Each block contains a hash pointer that points to the previous block of data. Each pointer then tells us where the data is and what the entire value of that block is. This will let us know if any data has been tampered with. And this shows a Merkle tree. It basically has all of the same features of the previous slide, but verification can be isolated to a certain branch and not the entire chain. This allows us to tell what blocks do or do not belong in this tree. Our next thing that we need to get a grasp on is digital signatures. And how do we know if a transaction is legit? Well, it must contain a digital signature. It's just like a written signature, only in a digital form. And here are some of the features of a digital signature. Only you can make your signature, but anyone who sees it can verify that it's valid. We also want the signature to be tied to a particular document so that the signature cannot be used to indicate your agreement or endorsement of a different document. And the final thing is unforgeable. We don't want anyone else to be able to digitally sign something of ours with our name. And this is what it looks like to generate a digital signature. You can see that this will generate, sign, and validate your signature. And I should note that this will generate a secret signing key as well as a public verification key. This is what allows us to sign, but anyone to verify. So, what kind of cryptography does Bitcoin use? It's called the elliptical curve digital signature algorithm, or the ECDSA for short. And it relies on some very complicated and unorthodox, hairy math. But the main point is good randomness is very important. If there's not good randomness, especially in the generate key or sign functions, you probably just leaked your key and now your signature can be forged. As we mentioned before, there are public keys that are generated in order for verification. You can equate these public keys to an identity. Now, this isn't a specific identity, such as your name, social security number, and address, but it's just something that can be inferred. In other words, if a signature is verified on a message, then you can infer that that message was said by that particular public key. And the thing about these identities are you can make a new identity anytime you want to. You don't need permission from anyone. You don't have to go register it. It's a very decentralized method. And in Bitcoin, these identities are known as addresses. Now, this decentralization and this concept kind of leads to how private is this? And as I said before, it doesn't lead to your true identity, but if you have several transactions or messages that all have your signature, people can start to assume that, hey, all of this seems to act just like John Doe would. This must be John Doe. Now, let's look at a very simple cryptocurrency called Goofy Coin. And this kind of puts all of the cryptography that we've talked about into use. Goofy Coin has a few properties that are seen here. Goofy can create new coins by simply signing a statement that he's making a new coin with a unique coin ID. And whoever owns a coin can pass it on to someone else by signing a statement that says, pass this on to X, where X is specified by a public key. Anyone can verify the validity of a coin by following the chain of hash pointers back to its creation by Goofy, verifying all of the signatures along the way. So we see here that Goofy originally created the coins. And then he paid one to Alice. Alice and then transferred that to Bob. All of that has a hash pointer that goes back to the original creation of Goofy. However, there are a few security issues with this type of setup. There's just not enough record with transfer, which can lead to double spending, which is the main problem with this type of coin. Now, what is double spending? Let's just say in the previous example that Alice has her coin. She gives it to Bob, but then immediately after that also attempts to give it to Fred. She doesn't really have the other one to give to Fred because she's already given it to Bob. So how do we prevent this? Well, let's look at another type of coin called Scrooge coin. The Scrooge will publish the history of all the transactions, and then it will be signed by Scrooge himself. This is the blockchain. And this history helps us track the attempt of double spending. So what it does is Scrooge will publish an append-only ledger containing the history of all the transactions that have happened. This, in turn, will ensure that any of the information written to the ledger remains forever. In Scrooge coin, a transaction only counts if it is in the blockchain signed by Scrooge. Anyone can verify that a transaction was endorsed by Scrooge by checking for his signature on the blockchain that it appeared in. This will create coin and pay coin in each transaction. This prevents a double spending. However, it is centralized, which leads us to the next problem that we will be talking about in a future event.